The German King Tiger, officially designated the Tiger II, was one of the heaviest and most complex tanks ever built during World War II. Conceived during the final phase of the conflict, it represented the peak of armored vehicle ambition at the time. Everything about it was extreme: its weight, its armor, its firepower, and the engineering effort required to make it move. From the outside, the King Tiger appears almost unstoppable. Thick, sloped armor plates form a sharp, intimidating silhouette. Its massive turret dominates the hull, giving the impression of a machine designed without compromise. But while history often focuses on how the King Tiger looked or what it could do on paper, the real story begins inside. Behind the steel walls was a cramped, mechanical environment shared by 5 crew members. Space was limited. Visibility was narrow. Heat, noise, and vibration were constant companions. Every lever, dial, and control had a purpose, and every action required coordination. The interior of the King Tiger was not built for comfort, it was built to serve a specific engineering philosophy. What was it really like to operate such a machine? How did its internal layout affect the crew? And how did the tank's complex systems shape both its strengths and its limitations? In this video, we step inside the King Tiger tank to explore those questions. Not to glorify war, and not to focus on destruction, but to understand the engineering, the mechanical systems, and the human experience inside one of history's most iconic armored vehicles. From the driver's position to the turret interior, from ammunition storage to the engine compartment, this is an inside look at the King Tiger, where steel, machinery, and human endurance came together in one extraordinary machine. The King Tiger entered service in 1944, during a period when World War II had reached its most intense and resource-strained phase. By this point, armored warfare had evolved dramatically from the early years of the conflict. Tanks were no longer simply infantry support vehicles, they had become the backbone of mobile warfare, tasked with engaging enemy armor, holding territory, and shaping the outcome of large-scale operations. The King Tiger, officially designated the Tiger II, was designed to dominate long-range engagements through a combination of heavy armor and powerful firepower. Its development reflected a belief that battlefield superiority could be achieved by outmatching opposing vehicles in protection and lethality. Engineers aimed to create a tank that could withstand enemy fire at distances where other vehicles would be vulnerable, while delivering accurate and effective fire in return. At first glance, the King Tiger appeared to embody this philosophy perfectly. Its sharply angled armor plates increased effective thickness, while its massive turret housed one of the most formidable tank guns of the era. On paper, it was capable of engaging enemy armor well before most opponents could respond effectively. This emphasis on long-range engagement shaped nearly every aspect of the tank's design. However, the King Tiger was also a product of late-war priorities. By 1944, Germany faced increasing pressure on all fronts, along with shortages of fuel, materials, and experienced personnel. Design decisions were often driven by urgency rather than balance. Maximum protection and firepower took precedence, even when those choices introduced serious trade-offs. One of the most significant consequences of this approach was weight. At nearly 70 tons, the King Tiger pushed the limits of what contemporary automotive technology could reliably support. Its engine, transmission, and drivetrain were required to move a vehicle far heavier than many systems were originally designed for. While the tank could perform impressively under ideal conditions, it was also prone to mechanical strain and breakdowns, especially during extended operations. Mobility was another area affected by these compromises. Although the King Tiger could reach respectable speeds on roads, its size and weight made it less flexible in difficult terrain. Narrow bridges, soft ground, and limited infrastructure posed constant challenges. Maneuvering such a large vehicle required careful planning and favorable conditions, factors that were not always available during late-war operations. The intended role of the King Tiger was not rapid exploitation or fast-moving assaults. Instead, it was envisioned as a breakthrough and defensive weapon. It was meant to hold key positions, counter enemy armor, and dominate open areas where long-range visibility favored its design strengths. In these scenarios, its armor and firepower could be fully utilized. Yet battlefield realities often differed from theoretical roles. Fuel shortages limited operational range. Spare parts were difficult to obtain. Maintenance demands were high, and trained crews were increasingly scarce. These factors meant that many King Tigers never operated under ideal circumstances, despite their impressive technical specifications. Understanding the King Tiger requires looking beyond its reputation and statistics. It was not simply a symbol of power, but a complex machine shaped by the pressures of time, resources, and strategic necessity. Every design choice reflected a specific problem engineers were trying to solve, even if the solution introduced new challenges elsewhere. The tank's design philosophy prioritized survivability above all else. Armor thickness was increased wherever possible, often resulting in a vehicle that could withstand hits that would disable other tanks. This emphasis on protection gave crews a degree of confidence, but it also came with psychological and physical costs. Operating inside such a massive machine required constant awareness of mechanical limits and environmental constraints. Firepower was the second pillar of the King Tiger's design. Its main gun was intended to neutralize threats at long distances, reducing the need for close-range engagements. This aligned with the broader doctrine of engaging enemy armor before it could effectively respond. However, achieving this level of firepower required additional space, weight, and complexity, further compounding mechanical demands. The interior layout of the King Tiger was directly influenced by these priorities. Crew positions, ammunition storage, and mechanical systems were arranged to support the main gun and armor scheme. Comfort and ease of movement were secondary considerations. Space was functional rather than generous, and every compartment served a specific purpose. From a historical perspective, the King Tiger represents a turning point in armored vehicle design. It illustrates the limits of pursuing maximum performance in isolated categories without equal consideration for logistics and sustainability. While its engineering achievements were remarkable, they also highlighted the importance of balance in vehicle design. It is also important to view the King Tiger within the broader context of the war's final years. By 1944, the strategic situation had changed significantly. Allied forces possessed overwhelming industrial capacity, allowing them to produce large numbers of reliable vehicles. In contrast, German designers were tasked with creating highly specialized machines under increasingly constrained conditions. This contrast shaped the King Tiger's legacy. Technically impressive, yet operationally demanding, it became both a symbol of engineering ambition and a case study in the challenges of late-war development. Its strengths were undeniable, but so were its limitations. Understanding why the King Tiger was built the way it was helps explain both its successes and its shortcomings. It was designed to solve specific tactical problems, not to be a universal solution. Its creators focused on immediate battlefield requirements, often at the expense of long-term practicality. As we move forward in this series, we will look beyond the overview and step inside the King Tiger itself. We'll examine how its design philosophy translated into the crew environment, how its mechanical systems functioned in practice, and how these factors shaped daily operation. By exploring the King Tiger from the inside out, we gain a clearer picture of what this tank truly represented. Not just a weapon, but a complex intersection of engineering, strategy, and human experience during one of history's most challenging periods. Understanding the King Tiger begins with understanding why it was built the way it was. And only by examining those choices can we fully appreciate the machine, the people who operated it, and the lessons it left behind. Inside the King Tiger, space was limited and carefully allocated. Every centimeter of the interior served a purpose, shaped by the need to support armor, firepower, and mechanical systems within a heavily protected hull. Unlike modern vehicles designed with crew comfort in mind, the King Tiger's internal layout reflected the realities of mid-20th century armored warfare, where functionality took precedence over ergonomics. The King Tiger was operated by a crew of 5. Each crew member had a clearly defined role, and successful operation depended on coordination, discipline, and familiarity with the tank's internal environment. The 5 positions included the commander, gunner, loader, driver, and radio operator. Together, they formed a tightly integrated team working within a confined mechanical space. The commander occupied a position in the turret, slightly elevated to provide better visibility. From this vantage point, the commander was responsible for situational awareness, coordination, and decision-making. Observation devices and periscopes allowed the commander to monitor surroundings, but visibility was limited compared to open environments. Clear communication with the rest of the crew was essential, as the commander relied on others to carry out instructions efficiently. Seated below and forward of the commander was the gunner. The gunner's role centered on aiming and firing the main gun, using optical sights mounted within the turret. The gunner's position was highly specialized, with controls arranged for quick access. Precision and focus were critical, as even small adjustments could significantly affect accuracy. The gunner worked closely with the commander to identify targets and align the weapon system. The loader occupied the opposite side of the turret. This position required physical strength and endurance, as the loader was responsible for handling heavy ammunition and preparing each round for use. Ammunition was stored throughout the turret and hull, and accessing it required careful movement in a confined space. The loader's efficiency directly influenced the tank's operational rhythm, making the role physically demanding and mentally focused. At the front of the hull sat the driver. The driver's compartment was narrow, with limited visibility provided by viewing ports and periscopes. Steering a vehicle as large and heavy as the King Tiger required constant attention and precise control. The driver managed speed, steering, and braking, often relying on verbal instructions from the commander due to restricted sightlines. Next to the driver was the radio operator. This crew member handled communications and assisted with hull-mounted equipment. The radio operator played a vital role in maintaining contact with other units and relaying information. In addition to communication duties, the radio operator often assisted with observation and internal coordination, especially during movement or positioning. Interior space within the King Tiger was constrained by thick armor plates and mechanical components. The hull and turret were designed to maximize protection, leaving little room for movement. Crew members often worked shoulder to shoulder, navigating around ammunition racks, structural supports, and mechanical housings. Movement inside the tank required awareness of both people and machinery. Ergonomics inside the King Tiger reflected the technological standards of the era. Seating was functional rather than comfortable, designed to keep crew members stable during movement. Seats were often adjustable only to a limited degree, and long periods inside the tank could be physically exhausting. Padding was minimal, and vibration from the engine and suspension transmitted throughout the interior. Controls were arranged based on mechanical necessity rather than human-centered design. Levers, pedals, and handwheels required strength to operate, particularly during extended use. The physical effort needed to drive or operate systems added to crew fatigue, especially during long missions or repeated maneuvers. Visibility inside the tank was restricted. Viewing ports and periscopes provided narrow fields of view, requiring crew members to rely heavily on communication and coordination. Situational awareness depended not only on what could be seen, but on information shared among the crew. This made teamwork essential to safe and effective operation. Noise was a constant presence inside the King Tiger. The engine, drivetrain, and mechanical systems produced high levels of sound, making verbal communication difficult. Crews often relied on shouted commands, hand signals, or internal communication systems. Prolonged exposure to noise contributed to physical strain and mental fatigue. Heat was another challenge. The engine compartment generated significant warmth, which spread throughout the interior. Ventilation was limited, and temperature could rise quickly during extended operation. Managing heat was part of daily life inside the tank, affecting concentration and endurance. Despite these conditions, the internal layout was carefully planned to support the tank's primary mission. Each crew position was located to optimize access to controls, weapons, or systems relevant to that role. Ammunition storage was placed to balance accessibility and space efficiency, even though it reduced overall room. The turret interior, in particular, was a dense concentration of equipment. The main gun breech, recoil systems, sights, and control mechanisms occupied much of the available volume. Crew members had to work around these components, often adapting their movements to avoid injury or interference with mechanical parts. The hull interior housed not only the driver and radio operator, but also essential mechanical systems. Driveshafts, fuel tanks, and structural supports reduced available space and shaped crew movement. The layout reflected a compromise between mechanical requirements and human operation. Living conditions inside the King Tiger were austere. Crews often spent extended periods inside the vehicle, sometimes remaining within the tank even when stationary. Personal space was minimal, and storage for personal items was limited. Comfort was secondary to readiness and functionality. Training played a critical role in adapting to these conditions. Familiarity with the interior layout allowed crews to operate efficiently despite constraints. Experienced crews developed routines and communication methods to overcome limited space and visibility. From a design perspective, the King Tiger's internal layout highlights the priorities of its creators. Protection, firepower, and mechanical capability dictated the structure, while human factors were accommodated within those constraints. This approach was common in heavy armored vehicles of the period. Understanding the crew environment inside the King Tiger provides valuable insight into how the tank functioned as a whole. It was not merely a machine, but a working environment that demanded physical endurance, coordination, and adaptability from its crew. As we move forward, examining specific systems and compartments in greater detail, the importance of internal layout and crew roles becomes even clearer. Every control, seat, and viewing port reflected the realities of operating a heavy tank in challenging conditions. The King Tiger's crew compartment was a place where engineering ambition met human limitation. By understanding this environment, we gain a deeper appreciation of how the tank was operated and what daily life inside it was truly like. The King Tiger's main gun was designed with one primary goal in mind: accuracy and long-range effectiveness. Rather than emphasizing rapid firing or close-range maneuver combat, the tank's armament reflected a philosophy of engaging targets at distance, where precision, optics, and ballistic performance could be fully utilized. At the center of the King Tiger's firepower was its large-caliber main gun, mounted within the massive turret. This weapon represented one of the most advanced tank guns of its era, designed to deliver high velocity and consistent accuracy. Its size and power influenced nearly every aspect of the tank's layout, from turret dimensions to internal storage and crew workflow. The gun itself was a complex mechanical system. The barrel, breech mechanism, recoil system, and mounting assembly worked together to manage the forces generated during firing. When the gun was discharged, the recoil system absorbed and redirected energy, allowing the barrel to return smoothly to its original position. This mechanical balance was essential for maintaining accuracy and preventing damage to internal components. Loading the main gun required coordination and physical effort. Ammunition was large and heavy, demanding careful handling by the loader. Each round had to be positioned correctly and seated into the breech before firing. This process emphasized deliberate, controlled operation rather than speed. The design favored careful shot placement over high rates of fire. The types of shells used by the King Tiger reflected its intended role. While the specifics of ammunition design are often discussed in technical detail, it is important to understand them at a high, educational level. Different shell types were developed to perform specific functions, such as engaging armored vehicles or addressing fortified positions. Each type had distinct characteristics in terms of weight, shape, and internal construction. Selecting the appropriate shell was a critical part of the firing process. The commander and gunner worked together to determine which round best suited the situation. This decision-making process highlighted the importance of communication and situational awareness inside the turret. Ammunition was stored in designated racks to ensure accessibility while minimizing interference with crew movement. Sighting systems played a central role in the King Tiger's emphasis on precision. Optical sights were mounted in alignment with the main gun, allowing the gunner to observe targets through magnified lenses. These optics were engineered to provide clarity at long distances, supporting the tank's role in long-range engagement. The gunner's sight was mechanically linked to the gun's elevation and traverse systems. Adjustments made through handwheels translated directly into precise movements of the gun. This mechanical connection ensured that visual alignment corresponded accurately with the weapon's orientation. Mastery of these controls required training and experience, as even small inputs could produce noticeable changes. The commander also had access to observation devices, including periscopes and vision blocks. While not directly responsible for aiming the gun, the commander played a crucial role in identifying targets and directing the gunner's attention. This separation of duties allowed the gunner to focus on precision while the commander maintained broader situational awareness. Fire control in the King Tiger was largely manual by modern standards. There were no computerized targeting systems or automated rangefinders. Instead, accuracy depended on optical clarity, crew judgment, and experience. Range estimation, target movement, and environmental conditions all had to be considered during engagement. This reliance on human skill underscored the importance of training. Crews who were familiar with their optics and weapon systems could achieve impressive accuracy, while inexperienced crews faced a steep learning curve. The mechanical design provided the tools, but effective use depended on the people inside the tank. In addition to the main gun, the King Tiger was equipped with secondary weapons. These included machine guns mounted in the hull and turret. The purpose of these secondary weapons was defensive and supportive rather than offensive dominance. They allowed the crew to respond to nearby threats and maintain awareness around the vehicle. Secondary weapons were operated by specific crew members, depending on mounting location. Controls were integrated into the tank's interior layout, allowing operation without significantly disrupting primary tasks. While less complex than the main gun, these systems still required coordination and attention. The placement of secondary weapons reflected practical considerations. Hull-mounted weapons covered forward areas, while turret-mounted systems provided flexibility. Together, they contributed to the tank's overall defensive capability, complementing the main armament without overshadowing it. The turret interior was heavily influenced by the armament system. The main gun's breech occupied significant space, shaping crew positioning and movement. Recoil mechanisms, elevation gears, and mounting structures surrounded the gun, creating a dense mechanical environment. Crew members had to remain aware of moving parts to avoid injury during operation. Ammunition handling added another layer of complexity. Shells were stored in multiple locations within the turret and hull, each chosen to balance accessibility and space constraints. Retrieving ammunition required physical movement and coordination, particularly in the confined turret environment. Safety considerations were an important aspect of armament design. Mechanical interlocks and procedures helped reduce the risk of accidental discharge. Crew training emphasized proper handling, communication, and adherence to firing protocols. From an engineering perspective, the King Tiger's armament system represented a trade-off between power and practicality. The gun's size and capability contributed to the tank's formidable reputation, but also increased weight and internal complexity. These factors influenced reliability, maintenance demands, and overall vehicle balance. Maintenance of the armament system required regular attention. The barrel, breech, and recoil components were subject to wear and needed inspection. Optical sights had to be kept clean and aligned to maintain accuracy. These tasks were essential for keeping the tank operational over time. The integration of optics and weapon systems reflected advanced thinking for the period. Designers recognized that firepower alone was insufficient without effective targeting. By combining a powerful gun with precise optical equipment, the King Tiger emphasized controlled engagement rather than sheer volume of fire. This focus on precision also shaped crew workflow. Engagements were deliberate processes involving observation, communication, adjustment, and execution. Each step relied on coordination between commander, gunner, and loader, highlighting the human element within the mechanical system. It is important to note that this chapter focuses on the mechanical and optical systems themselves, not combat tactics or battlefield outcomes. Understanding how the armament function provides insight into the tank's design philosophy without emphasizing destruction or violence. The King Tiger's fire control system illustrates the technological limits and achievements of its time. Without automation, crews relied on mechanical linkages, optics, and experience. This approach demanded skill and discipline, but also allowed for remarkable accuracy when conditions were favorable. Comparing these systems to modern equivalents highlights how far technology has advanced. Yet, the fundamentals of observation, alignment, and control remain relevant. The King Tiger serves as a historical example of how engineering solutions addressed the challenges of armored warfare in the mid-20th century. Ultimately, the armament and fire control systems were central to the King Tiger's identity. They shaped its reputation, influenced its operational role, and defined the internal layout of the turret. Understanding these systems helps explain both the strengths and limitations of the tank as a whole. As we continue this series, we will shift focus from weapons to protection, examining how armor design, hull structure, and turret construction work together to support the King Tiger's overall concept. By exploring each system in detail, we gain a clearer picture of how this complex machine functioned from the inside out. The King Tiger's armor was among the thickest and most formidable of its era. From the earliest stages of its design, protection was treated as a primary requirement rather than a secondary consideration. Engineers aimed to create a vehicle capable of surviving hits that would disable or destroy other tanks, especially during long-range engagements where heavy armor could provide a decisive advantage. Armor layout on the King Tiger followed a carefully planned structure. Rather than relying solely on raw thickness, designers incorporated angled surfaces to increase effective protection. By sloping armor plates, incoming projectiles were more likely to be deflected or forced to penetrate a greater thickness of material. This approach allowed the tank to achieve higher survivability without proportionally increasing armor mass in every area. The frontal armor of the hull was especially emphasized. The glassy plate, positioned at a sharp angle, became one of the most recognizable features of the King Tiger's design. This sloped surface combined thickness with geometry to maximize resistance. From an engineering standpoint, it represented a shift toward more advanced armor concepts that balanced material use and protective effectiveness. Side armor was also substantial, though not as heavily reinforced as the front. Designers recognized that frontal engagements were the most likely scenario in which armor would be tested. Side and rear protection, while still significant, reflected a compromise between weight and coverage. Even so, the King Tiger's side armor exceeded that of many contemporary vehicles. The use of thick armor throughout the hull contributed to the tank's immense weight. At nearly 70 tons, the King Tiger pushed the limits of what could reasonably be supported by mid-20th century automotive technology. Every additional plate of steel added protection, but also placed strain on the engine, drivetrain, and suspension systems. The hull itself served as the structural backbone of the tank. Constructed from large welded and interlocked armor plates, it housed essential systems such as the driver's compartment, radio operator's position, fuel storage, and drivetrain components. The hull's design prioritized rigidity and strength, ensuring that it could support both the turret and the stresses of movement. Internally, the hull's armored structure shaped crew space and system placement. Thick armor reduced available interior volume, creating a confined working environment. Structural supports, weld seams, and reinforcement elements were visible inside, reminding crew members that protection came at the cost of space and flexibility. Angled surfaces were not limited to the front of the hull. Side plates and rear armor also incorporated slopes where possible. This design philosophy reflected lessons learned earlier in the war, where sloped armor had proven more effective than vertical plates of equal thickness. The King Tiger applied these principles on a larger and heavier scale. The turret was perhaps the most visually dominant element of the King Tiger. Massive and imposing, it housed the main gun, fire control systems, and 3 of the 5 crew members. Turret design was closely linked to both armament requirements and armor protection. Accommodating the large main gun required a spacious internal structure, while thick armor ensured survivability. Early and later production turrets differed slightly in shape, but both emphasized heavy frontal protection. The turret front featured thick, angled armor designed to withstand direct hits. The sides and rear of the turret were also well protected, though less heavily reinforced than the front. This balance reflected the expectation that frontal engagements posed the greatest threat. Internally, the turret was a dense mechanical environment. Armor thickness reduced internal space, leaving little room beyond what was required for the gun, recoil system, and crew stations. Crew members operated in close proximity to moving mechanical parts, making awareness and coordination essential. The turret ring, which allowed the turret to rotate, was a critical structural component. Supporting the weight of such a massive turret required precise engineering. The ring had to maintain smooth rotation while bearing enormous loads, even when the tank was traversing uneven terrain. Any damage or misalignment could severely affect turret operation. Armor distribution across the turret was carefully considered. The front offered maximum protection, while the sides and rear balanced coverage with weight savings. Roof armor, while thinner than other sections, still provided protection against indirect threats and environmental hazards. One of the defining trade-offs of the King Tiger's armor design was mobility. Heavy armor improved survivability but reduced speed, agility, and operational flexibility. Crossing bridges, navigating soft ground, or maneuvering in confined spaces became significant challenges. These limitations were a direct consequence of prioritizing protection above all else. From a survivability perspective, the King Tiger's armor could provide crews with a sense of security. Thick plates and angled surfaces increased the likelihood that the tank could withstand enemy fire. However, this protection also encouraged engagement scenarios where the tank relied on armor rather than mobility to survive. Manufacturing such heavy armor was resource-intensive. Producing large, thick plates required significant industrial capacity, skilled labor, and high-quality materials. By 1944, these resources were increasingly scarce. As a result, production quality and consistency could vary, further complicating maintenance and repair. Welding and assembly techniques played a critical role in armor effectiveness. Proper alignment and joining of plates were essential to maintaining structural integrity. Weak points at weld seams or joints could compromise protection, emphasizing the importance of manufacturing precision. The hull and turret together formed a protective shell around the crew and vital systems. This shell was not just passive armor, but an integral part of the tank's overall design philosophy. Every angle, thickness, and joint reflected an effort to maximize survivability within technological constraints. However, armor alone could not guarantee safety. Mechanical reliability, crew training, and operational context all influenced how effective the King Tiger's protection proved in practice. A heavily armored tank that could not move or be maintained effectively faced its own risks. The psychological impact of armor should not be overlooked. Operating inside a heavily armored vehicle could influence crew behavior, decision-making, and confidence. Knowing that the tank offered substantial protection may have affected how crews approached movement and positioning. From a modern perspective, the King Tiger's armor design illustrates both innovation and limitation. Angled plates and thick armor were forward-thinking, but the resulting weight and complexity highlighted the importance of balance in armored vehicle design. The hull and turret were not independent elements, but parts of a unified system. Changes to one affected the other. Increasing turret armor added strain to the hull and suspension, while hull design influenced turret placement and rotation. As we examine the King Tiger today, its armor remains one of its most defining features. The sheer scale of protection is immediately apparent, even to casual observers. Yet understanding the reasons behind this design reveals a more nuanced story. The King Tiger's armor prioritized survivability in an era when firepower was rapidly increasing. Designers responded by building thicker, stronger, and more complex protective structures. These choices reflected both technological ambition and strategic necessity. At the same time, the limitations imposed by this approach became clear. Weight reduced mobility. Complexity increased maintenance demands. Production challenges limited numbers. The armor that made the King Tiger formidable also made it difficult to deploy effectively. In the context of armored vehicle development, the King Tiger represents an extreme example of protection-focused design. It stands as a case study in how far armor can be pushed before trade-offs outweigh benefits. Understanding the armor, hull, and turret of the King Tiger helps explain the tank's overall character. It was built to endure, to absorb punishment, and to protect its crew in the harshest conditions. But it was also constrained by the very features that made it unique. As we move forward, we will shift attention from protection to internal systems and storage, exploring how ammunition, equipment, and mechanical components were arranged within this armored shell. By continuing this inside-out approach, we gain a deeper understanding of how the King Tiger functioned as a complete machine. Ammunition storage inside the King Tiger was carefully planned to balance accessibility, safety, and the severe space limitations imposed by heavy armor and large mechanical systems. Every round carried inside the tank represented both capability and risk. Designers were tasked with ensuring that ammunition could be accessed efficiently by the crew while minimizing interference with movement and reducing the potential hazards associated with storing large quantities of explosive material inside an armored vehicle. The King Tiger carried ammunition primarily for its main gun, with additional supplies for secondary weapons. Main gun rounds were large, heavy, and required deliberate handling. Their size alone dictated much of the tank's internal layout. Unlike smaller vehicles where ammunition could be stored in centralized racks, the King Tiger distributed its ammunition across multiple locations within the turret and hull. One of the primary storage areas was within the turret itself. Storing ammunition close to the gun reduced the distance the loader needed to move during operation. This proximity allowed for smoother workflow and reduced physical strain during loading. However, turret space was extremely limited, and only a portion of the total ammunition supply could be stored there. Additional rounds were stored in racks along the hull interior. These racks were typically positioned along the sides of the fighting compartment, secured within armored recesses. Hull storage provided increased capacity but required the loader to move further and coordinate closely with other crew members. Accessing these rounds often depended on the tank's orientation and internal activity at the time. Each round had a designated location within the tank. This organization was critical. In the confined environment of the King Tiger, searching for ammunition would waste valuable time and increase fatigue. By assigning specific positions to each round, crews could develop routines that allowed for faster and safer handling under pressure. Crew access to ammunition was shaped by both design and training. The loader's position within the turret was carefully chosen to provide access to nearby racks while avoiding interference with the gun's recoil and movement. The loader needed to maintain awareness of the gun's position at all times, as recoil systems occupied much of the available space. Handling ammunition inside the King Tiger was physically demanding. Each round required careful lifting, positioning, and insertion into the breech. The confined interior meant that movements had to be controlled and precise. Sudden shifts or loss of balance could result in injury or interference with equipment. Coordination among crew members was essential during ammunition handling. The commander, gunner, and loader needed to communicate clearly to ensure that the correct type of round was selected and prepared. Miscommunication could slow operation or create unsafe conditions. This reliance on teamwork highlighted the human element within the tank's mechanical systems. Safety considerations were central to ammunition storage design. Racks were constructed to secure rounds firmly, preventing movement during travel over uneven terrain. Clamps and supports held each shell in place, reducing the risk of damage to casings or fuses. Proper storage also minimized the chance of accidental ignition due to impact or vibration. The placement of ammunition took into account the tank's armor layout. Designers aimed to position rounds behind thick armor wherever possible, reducing vulnerability. Hullside racks were often shielded by external armor plates, while turret storage benefited from the turret's heavy protection. This approach reflected an understanding of how incoming fire might affect internal safety. Despite these precautions, storing ammunition inside a tank always carried inherent risk. The King Tiger's designers recognized this and implemented procedures to mitigate danger. Crew training emphasized careful handling, adherence to loading protocols, and awareness of environmental conditions inside the tank. Secondary weapon ammunition was stored separately from main gun rounds. Machine gun ammunition was typically housed in smaller containers or boxes, positioned for easy access by the appropriate crew member. These supplies took up less space but still required organization to avoid clutter and interference with primary systems. The interior layout of ammunition storage influenced crew movement patterns. Narrow passages between racks and equipment meant that crew members had to memorize routes and adapt their posture when moving inside the tank. Over time, experienced crews developed efficient ways to navigate the interior without disturbing stored rounds. Temperature and ventilation also affected ammunition storage. Heat generated by the engine and mechanical systems could raise interior temperatures significantly. Designers had to consider how heat might affect ammunition stability over prolonged periods. Ventilation systems helped manage internal conditions, though comfort was limited. In practice, ammunition management was a continuous task. Crews monitored remaining supplies, adjusted storage usage, and ensured that rounds were secured after movement or repositioning. This constant attention reflected the importance of ammunition as both a resource and a responsibility. The distribution of ammunition storage also influenced the tank's balance. Placing heavy rounds in specific locations affected weight distribution within the vehicle. Designers had to consider how this weight would shift as ammunition was expended, potentially altering handling characteristics over time. Maintenance routines included inspection of ammunition racks and storage mechanisms. Clamps, brackets, and supports were checked for wear or damage. Ensuring that storage systems remained secure was essential for safe operation, especially during long movements or rough terrain. From an ergonomic perspective, ammunition storage inside the King Tiger represented a compromise. Accessibility was necessary for effective operation, but space constraints limited ideal placement. The resulting layout demanded physical endurance and situational awareness from the crew, reinforcing the demanding nature of armored vehicle operation. The loader's role was particularly shaped by storage design. Efficient ammunition handling required strength, coordination, and familiarity with storage locations. The loader's performance directly influenced the tank's operational rhythm, making this position one of the most physically demanding inside the vehicle. Crew training emphasized repetition and routine. By practicing loading procedures and movement patterns, crews could reduce errors and improve efficiency. Familiarity with storage layout allowed for smoother operation even under challenging conditions. The King Tiger's ammunition storage system reflected broader design priorities. Protection and firepower were paramount, and storage solutions were developed to support these goals within tight constraints. While not optimized for comfort or ease, the system was functional and purpose-driven. From a historical perspective, examining ammunition storage offers insight into the practical realities of operating heavy tanks during World War II. It highlights the balance between engineering ambition and human capability. Every design choice influenced how the crew interacted with the machine. Comparing the King Tiger's storage systems to those of later vehicles reveals how lessons were learned over time. Modern designs place greater emphasis on crew safety, compartmentalization, and ergonomic access. The King Tiger represents an earlier stage in this evolution. Understanding ammunition storage also helps explain some of the tank's limitations. Restricted space and heavy rounds slowed operation and increased fatigue. These factors affected sustained performance, particularly during extended deployments. Despite these challenges, the storage system allowed the King Tiger to fulfill its intended role. Ammunition was accessible, organized, and protected to the extent possible given the technology and constraints of the era. The system supported the tank's emphasis on deliberate, precise engagement. The relationship between ammunition storage and overall vehicle design was inseparable. Storage influenced turret layout, crew positioning, and internal movement. Changes to one system affected others, reinforcing the interconnected nature of armored vehicle engineering. As we step back and view the King Tiger as a complete system, ammunition storage emerges as a critical component. It was not merely about holding rounds, but about enabling coordinated operation within a confined and demanding environment. In the next chapter, we will shift focus from storage to power, examining how the engine, fuel systems, cooling, and fire safety equipment work together to move and sustain this massive armored vehicle. By continuing this inside-the-machine approach, we gain a deeper understanding of how the King Tiger functioned in real-world conditions. Powering a vehicle of the King Tiger's size and weight required a complex and carefully integrated engine system. At nearly 70 tons, the tank placed extraordinary demands on its propulsion components. Every aspect of the engine, fuel delivery, cooling, and fire safety systems was designed to support sustained operation under heavy mechanical stress. At the heart of the King Tiger was a large gasoline engine mounted in the rear of the hull. This engine was derived from earlier designs but adapted to meet the increased demands of a heavier vehicle. While powerful for its time, it was still operating near the upper limits of what contemporary engineering could reliably provide. Moving such a massive armored vehicle required careful balancing of power output, durability, and fuel consumption. The engine compartment was densely packed with mechanical components. Space was limited by thick rear armor and structural supports, leaving little room for excess capacity or redundancy. The engine itself was connected to the drivetrain through a series of shafts and couplings, transmitting power forward to the transmission and final drive systems. Any inefficiency or mechanical issue could quickly affect overall performance. Fuel delivery was a critical concern. The King Tiger consumed fuel at a high rate, particularly during movement over rough terrain or sustained operation. Fuel tanks were integrated into the hull, positioned to balance weight distribution while remaining protected by armor. These tanks fed the engine through a network of lines, pumps, and filters designed to maintain steady flow under varying conditions. Managing fuel inside a combat vehicle carried inherent risks. Designers had to ensure that fuel lines were shielded as much as possible from damage, heat, and vibration. Secure mounting and careful routing reduced the likelihood of leaks or failures. Even so, fuel management required constant attention from the crew, particularly during long op ratio. Cooling the engine was one of the most significant challenges. The King Tiger's engine generated substantial heat, and failure to dissipate that heat effectively could lead to reduced performance or mechanical damage. To address this, the tank was equipped with a dedicated cooling system that included radiators, fans, and airflow channels. Air intake and exhaust systems were carefully designed to support cooling while minimizing vulnerability. Air had to be drawn into the engine compartment, circulated across hot components, and expelled efficiently. This process relied on both mechanical fans and the movement of the vehicle itself. Any obstruction or malfunction could quickly result in overheating. The cooling system operated continuously during engine use, and its effectiveness depended on maintenance and environmental conditions. Dust, debris, and heat buildup could reduce airflow and efficiency. Crews needed to monitor engine temperature closely and adjust operation as needed to prevent damage. Ventilation within the engine compartment also affected the crew environment. Heat from the engine radiated forward into the fighting compartment, contributing to elevated interior temperatures. While insulation and airflow channels helped reduce heat transfer, conditions inside the tank could still become uncomfortable during extended use. Fire safety was an essential consideration in engine design. The combination of fuel, heat, and confined space created a potential hazard. To mitigate this risk, the King Tiger was equipped with onboard fire suppression equipment. Fire extinguishers were strategically placed for access by the crew, allowing rapid response in the event of an engine or fuel fire. The fire suppression system was primarily manual, relying on crew action rather than automatic detection. Training emphasized quick recognition of warning signs such as smoke, unusual smells, or temperature spikes. Immediate response could prevent minor issues from escalating into serious damage. Extinguishers were designed to be used in confined spaces, targeting specific areas of concern. Their placement reflected likely fire sources, including the engine compartment and fuel storage areas. Accessibility was critical, as delays could have severe consequences. Engine operation required careful coordination with other systems. Starting the engine involved multiple steps, including fuel priming, ignition, and monitoring of gauges. Once running, the engine's performance influenced everything from vehicle speed to electrical power generation. Electrical systems were powered in part by the engine, supplying energy for lighting, communication equipment, and other onboard systems. This interdependence meant that engine issues could affect multiple aspects of tank operation. Maintaining reliable engine function was therefore essential not only for movement, but for overall functionality. Fuel consumption imposed practical limitations on operational range. The King Tiger required frequent refueling, especially during intensive movement. Fuel logistics became a significant consideration, as transporting and storing gasoline safely was challenging under wartime conditions. The placement of fuel tanks within the hull reflected a compromise between capacity and protection. Tanks needed to hold sufficient fuel for meaningful range while remaining shielded by armor. Designers positioned them away from the most exposed areas, though absolute protection was impossible. Maintenance of the engine and fuel systems was demanding. Accessing components often required removing panels or working in cramped spaces. Routine inspections were necessary to identify leaks, worn parts, or cooling issues. Crews relied on regular maintenance to keep the vehicle operational. The engine's performance was also affected by terrain. Moving uphill, traversing soft ground, or operating in extreme temperatures increased strain. Under these conditions, careful throttle control and monitoring were essential to avoid overheating or mechanical failure. Cooling efficiency varied with speed and environment. Higher speeds increased airflow, improving cooling, while slow movement or idling reduced effectiveness. In hot climates or confined areas, managing engine temperature became particularly challenging. The King Tiger's engine system illustrates the trade-offs inherent in heavy vehicle design. While capable of moving a massive armored platform, it operated close to its limits. This left little margin for error and increased the importance of proper operation and maintenance. From a design standpoint, the integration of engine, fuel, cooling, and fire safety systems reflected an effort to balance performance with survivability. Each system supported the others, forming an interconnected network essential to the tank's function. Despite careful engineering, reliability issues were not uncommon. Mechanical strain, limited resources, and production variability affected performance. These challenges highlighted the difficulty of sustaining such a complex machine under demanding conditions. The crew's experience was shaped by these systems. Noise, heat, and vibration from the engine influenced daily life inside the tank. Awareness of engine condition became second nature, as changes in sound or temperature could signal emerging problems. Training emphasized understanding engine behavior. Crews learned to recognize normal operating characteristics and respond to irregularities. This knowledge helped prevent minor issues from escalating into failures. The fire suppression system provided a measure of reassurance, but it was not a substitute for careful operation. Preventing fires through proper maintenance and monitoring remained the primary defense. Looking at the King Tiger today, its engine and support systems offer insight into the limits of wartime engineering. Designers achieved remarkable results within technological constraints, but the complexity of the system introduced vulnerabilities. Comparing these systems to modern armored vehicles reveals significant advancements. Modern engines are more efficient, cooling systems more robust, and fire suppression more automated. The King Tiger represents an earlier stage in this technological evolution. Understanding the engine, fuel, and cooling systems helps explain the tank's operational strengths and weaknesses. Power enabled movement and function, but sustaining that power required constant attention and support. As we continue this exploration, we will move from power generation to control, examining how engine output was translated into motion through driving controls, transmission, and drivetrain systems. By following the flow of energy through the vehicle, we gain a deeper appreciation of how the King Tiger operated as a complete machine. Starting the King Tiger was not a simple turn of a key action. It was a deliberate, multi-step mechanical process that reflected the complexity and scale of the vehicle. Bringing a 70-ton armored machine to life required preparation, coordination, and a clear understanding of its systems. For the crew, especially the driver, engine startup marked the transition from a static machine to a moving system under constant mechanical strain. Before the engine could be started, several preliminary checks were required. Fuel levels had to be confirmed, oil pressure inspected, and cooling systems verified as functional. These steps were essential to prevent damage during startup, as the engine operated close to its performance limits. Skipping or rushing these checks could result in immediate mechanical problems. The driver played the central role in the startup process. Seated at the front of the hull, the driver faced a compact and utilitarian control layout. The interface was functional rather than intuitive, designed around mechanical necessity rather than ergonomic comfort. Levers, pedals, gauges, and switches surrounded the driver, each corresponding to a specific system. Starting the engine involved engaging fuel delivery, initiating ignition, and monitoring system response. The driver listened closely to the sound of the engine as it came to life. Changes in pitch, vibration, or response could indicate issues requiring immediate attention. Sound and feel were as important as visual indicators, making experience invaluable. Once the engine was running, gauges became the driver's primary reference. Oil pressure, engine temperature, and other indicators needed to stabilize within acceptable ranges before movement could begin. These readings provided reassurance that the engine was functioning correctly and that cooling systems were actively managing heat. The driver interface in the King Tiger reflected the realities of heavy vehicle operation. Steering was controlled through mechanical systems that required physical effort. Unlike modern power-assisted steering, the driver relied on strength and technique to maneuver the vehicle. Steering inputs were deliberate and required anticipation, particularly at low speeds. Braking was equally demanding. The mass of the King Tiger meant that stopping required careful planning. Brake pedals were firm, and braking force had to be applied progressively to maintain control. Sudden or uneven braking could place additional stress on mechanical components. Speed control was managed through throttle input and gear selection. Acceleration was gradual, reflecting both the weight of the tank and the need to protect the drivetrain. Rapid acceleration was neither practical nor advisable. Smooth, controlled inputs helped reduce wear and maintain stability. The control layout was dense but logically arranged. Levers for steering, gear selection, and braking were positioned within reach, though operating them simultaneously could be physically taxing. The driver's seat offered limited adjustability, and long periods at the controls required endurance. Visibility from the driver's position was restricted. Viewing ports and periscopes provided narrow fields of view, requiring constant attention and reliance on instructions from the commander. The driver often navigated based on verbal cues, adjusting direction and speed according to guidance from inside the turret. Communication between driver and commander was critical. The commander provided directions, speed adjustments, and situational awareness. Clear, concise communication helped compensate for limited visibility and reduced the risk of misjudgment. The process of putting the tank into motion required careful coordination. Once systems were stable, the driver engaged the transmission and began moving slowly. Initial movement allowed the crew to confirm that steering, braking, and drivetrain response were functioning as expected. Operating the King Tiger demanded both physical strength and mental focus. Steering levers resisted movement, pedals required firm pressure, and prolonged operation led to fatigue. Drivers had to manage their energy while maintaining precise control over a powerful machine. Gear changes were deliberate actions. Shifting gears required timing and coordination to avoid stressing the transmission. Smooth transitions helped maintain momentum and reduce mechanical strain. Experience played a key role in mastering these movements. The driver's workload increased significantly in challenging terrain. Uneven ground, inclines, and obstacles demanded constant adjustments. Steering corrections, throttle control, and braking all had to be balanced to maintain traction and stability. Noise and vibration were constant companions. The engine's sound filled the hull, and vibrations transmitted through the controls and seat. Over time, drivers learned to interpret these sensations, using them as feedback on vehicle condition. Heat from the engine affected the driver's environment. Even with ventilation, temperatures inside the hull could rise, especially during extended operation. Managing discomfort while maintaining concentration was part of the driver's daily experience. The startup and control systems also influenced the pace of operations. Bringing the tank to readiness took time, and rapid redeployment was not always possible. This characteristic shaped how the King Tiger was used operationally. Training was essential for effective control. Drivers needed familiarity with control resistance, response times, and system behavior. Repetition helped build muscle memory, allowing smoother operation even under stress. Mechanical reliability depended heavily on proper control use. Abrupt steering, harsh braking, or improper gear changes increased wear and risk of failure. Skilled drivers learned to operate within the tank's limits, extending component life. The driver interface did not isolate the driver from the rest of the crew. Coordination remained constant. Commands, acknowledgements, and updates flowed continuously, ensuring that movement aligned with tactical and mechanical considerations. Emergency procedures were part of training. Drivers needed to know how to shut down systems quickly if problems arose. Rapid response could prevent minor issues from escalating into serious damage. Despite its challenges, the control system provided a direct connection between human input and mechanical response. The absence of automation meant that the driver's skill had a direct impact on performance. This relationship emphasized the human element within the machine. From an engineering perspective, the startup and control systems reflected a balance between available technology and operational demands. Designers prioritized robustness over ease of use, accepting physical demands as a trade-off for durability. Comparing these controls to modern vehicles highlights significant advances in ergonomics and assistance. Power steering, automated transmissions, and digital interfaces have transformed driver experience. The King Tiger represents an earlier era, where mechanical systems dominated. Understanding engine startup and controls provides insight into daily life inside the tank. It reveals the physical and mental demands placed on the driver and underscores the importance of teamwork. The process of starting and controlling the King Tiger was as much about discipline as mechanics. Careful preparation, smooth operation, and constant awareness were essential to keeping the vehicle functional. As the tank moved, the driver remained alert to changes in behavior. Unusual sounds, resistance, or temperature shifts required immediate attention. The driver's awareness served as an early warning system for mechanical issues. The control layout also influenced interior movement. Levers and pedals occupied significant space, limiting foot and leg movement. The confined position required drivers to adapt their posture for comfort and efficiency. Long missions tested endurance. Maintaining focus while managing heavy controls demanded resilience. Brakes were limited, and fatigue was a constant factor. Despite these challenges, skilled drivers developed confidence in their ability to manage the vehicle. Familiarity bred efficiency, allowing smoother operation even under difficult conditions. The King Tiger's startup and control systems illustrate the broader theme of the vehicle, ambition balanced by limitation. Power and capability came with complexity and physical demand. Understanding these systems helps explain why operation required trained crews and careful planning. The tank was not forgiving of mistakes, and successful use depended on discipline and experience. As we move to the next chapter, we will follow the flow of power beyond the controls, examining how engine output was transmitted through the drivetrain and suspension. By continuing this mechanical journey, we gain a deeper understanding of how the King Tiger translated power into motion across varied terrain. The drivetrain of the King Tiger was responsible for translating engine power into movement, delivering torque from the engine to the massive steel tracks that carried the tank across varied terrain. Supporting this system was a complex suspension designed to bear extreme weight while maintaining stability. Together, these components made movement possible, but they also introduced significant mechanical challenges. Power generated by the engine traveled forward through a driveshaft to the transmission system. Unlike many modern vehicles, the King Tiger's transmission was positioned toward the front of the hull. This layout required a long driveshaft running beneath the fighting compartment, adding complexity to internal design and maintenance. The transmission itself was a large, mechanically intricate unit designed to handle immense loads. It provided multiple forward gears and reverse options, allowing the driver to adjust speed and torque based on terrain and operational needs. Gear selection was entirely manual, relying on precise timing and coordination from the driver to prevent undue strain. Operating the transmission required careful technique. Shifting gears under such weight demanded smooth inputs, as abrupt changes could cause mechanical shock. Improper shifting increased wear on gears, clutches, and bearings, reducing reliability over time. From the transmission, power was delivered to the final drive units. These components reduced rotational speed while increasing torque, enabling the tracks to move the tank's massive weight. Final drives were critical to overall mobility and were among the most stressed parts of the drivetrain. The King Tiger's tracks were wide and robust, designed to distribute weight and reduce ground pressure. This helped prevent the tank from sinking into soft terrain, such as mud or snow. However, the sheer mass of the vehicle still limited where it could operate effectively. Track links were heavy steel components connected by pins. Each link had to withstand enormous forces during movement, turning, and braking. Over time, pins and links experienced wear, requiring regular inspection and replacement to maintain functionality. Suspension played a vital role in managing these forces. The King Tiger used an overlapping road wheel suspension system, a design intended to distribute weight evenly and provide a smoother ride over uneven ground. Multiple rows of interleaved wheels supported each track, spreading load across a larger surface area. This suspension system offered advantages in stability and ride quality. By overlapping wheels, engineers reduced ground pressure and improved traction. The tank could move more steadily across rough terrain, minimizing excessive jolts to the hull and crew. However, the complexity of the suspension introduced maintenance challenges. The overlapping arrangement meant that accessing inner wheels often required removing outer ones. In muddy or icy conditions, debris could become trapped between wheels, increasing friction and wear. Each road wheel was connected to a torsion bar suspension. Torsion bars ran across the hull, twisting under load to absorb shocks. This design allowed for relatively smooth movement compared to earlier suspension types, but it also required precise manufacturing and alignment. The torsion bars were under constant stress. Repeated impacts from rough terrain could fatigue these components, leading to failure if not properly maintained. Replacing a damaged torsion bar was labor-intensive, often requiring significant disassembly. Ride characteristics inside the King Tiger reflected both the strengths and limitations of the suspension. On relatively even ground, movement could be surprisingly stable for such a heavy vehicle. Over rough terrain, however, the weight amplified impacts, transmitting vibration through the hull. Crew members experienced constant motion. Even with suspension damping, the mass of the tank meant that bumps were felt throughout the interior. Seats and supports offered limited cushioning, making prolonged movement physically demanding. Turning the King Tiger placed additional strain on the drivetrain. Steering involved differential power distribution between tracks, requiring precise control. Tight turns increased stress on track links, final drives, and suspension components. The drivetrain's forward placement influenced internal layout. The driveshaft running beneath the fighting compartment restricted space and dictated crew movement. Any maintenance on this system affected multiple internal areas. Lubrication was essential for drivetrain longevity. Gears, bearings, and joints required regular lubrication to reduce friction and heat. Insufficient lubrication accelerated wear and increased the likelihood of mechanical failure. Environmental conditions heavily influenced drivetrain performance. Mud, dust, snow, and debris could enter exposed components, affecting track movement and suspension efficiency. Crews had to remain vigilant, clearing debris when possible to prevent damage. Cold weather introduced additional challenges. Metal components contracted, lubricants thickened, and suspension response changed. Starting movement in cold conditions placed extra stress on drivetrain components until systems warmed up. Heat was another factor. Extended movement generated significant heat in the transmission and final drives. Without adequate cooling and rest periods, overheating could occur, reducing efficiency and increasing wear. Maintenance demands were high. Regular inspections were necessary to identify worn track links, damaged wheels, or stressed suspension elements. Given the King Tiger's complexity, maintenance required time, tools, and trained personnel. The overlapping roadwheel system, while effective in theory, proved difficult to maintain under operational conditions. Mud and ice accumulation between wheels could freeze or harden, restricting movement and increasing resistance. Despite these challenges, the suspension system contributed to the tank's ability to carry extreme weight. Without such a design, supporting nearly 70 tons would have been impractical with the technology of the era. The drivetrain also influenced fuel consumption. High rolling resistance from tracks and suspension components increased demand on the engine, contributing to heavy fuel usage. This further limited operational range and flexibility. Weight distribution across the suspension was carefully calculated. Designers aimed to balance the tank to prevent excessive stress on individual wheels or torsion bars. As ammunition and fuel were expended, weight distribution changed, subtly affecting handling. The crew adapted to the vehicle's ride characteristics. Drivers learned to anticipate terrain changes, adjusting speed and steering to minimize shock and strain. Experience improved smoothness and reduced mechanical stress. From a design perspective, the drivetrain and suspension reflect the King Tiger's overarching philosophy: prioritize capability, even if complexity increases. Engineers accepted maintenance challenges as a trade-off for performance. These systems also highlight the limits of mechanical engineering at the time. While innovative, they operated near the edge of reliability under real-world conditions. Sustaining performance required constant care. Comparing the King Tiger to lighter vehicles of the era underscores these trade-offs. Lighter tanks often sacrificed protection for mobility and ease of maintenance. The King Tiger took the opposite approach. The suspension's influence extended beyond comfort. Stable movement improved firing accuracy by reducing hull motion during short halts. This indirectly supported the tank's emphasis on long-range precision. However, any failure in the drivetrain or suspension could immobilize the vehicle. A broken final drive, damaged torsion bar, or thrown track rendered the tank stationary, regardless of armor or firepower. Recovery of such a heavy vehicle was difficult. Towing required specialized equipment, and field repairs were often impractical. This reality increased the importance of preventative maintenance. The interdependence of drivetrain components meant that small issues could escalate. A worn track link could stress wheels, which in turn affected suspension alignment. Crews needed to identify problems early. Noise and vibration from the drivetrain were constant. The clatter of tracks, whine of gears, and vibration of moving parts filled the interior, contributing to fatigue and sensory overload. Despite all this, the King Tiger could move across terrain that challenged many vehicles. Its wide tracks and robust suspension allowed it to traverse ground that might stop wheeled vehicles entirely. From a historical viewpoint, the drivetrain and suspension illustrate the ambition behind the King Tiger. Designers sought to overcome physical limits through engineering complexity, accepting the consequences. These systems also shaped how the tank was used operationally. Routes had to be planned carefully, avoiding terrain that would overstrain components or risk immobilization. Modern armored vehicles have learned from these experiences. Simpler suspension layouts, improved materials, and advanced engineering reduce maintenance burden while preserving capability. The King Tiger stands as a transitional design. Its drivetrain and suspension pushed boundaries, revealing both potential and limitation. Understanding these systems helps explain why the tank was both impressive and problematic. Movement was possible, but never simple. As we move into the next chapter, we will examine how these mechanical realities influenced real-world operation, focusing on how the King Tiger was actually used and what limitations crews encountered in service. By continuing this exploration, we gain a clearer picture of how engineering decisions shaped the tank's legacy. While formidable on paper, the King Tiger faced significant logistical and mechanical limitations in real-world operation. Its story is not only about strength and capability, but about the constant tension between engineering ambition and the practical realities of wartime use. Understanding how the King Tiger was actually employed helps explain why its legacy is as complex as the machine itself. The operational role envisioned for the King Tiger differed from that of lighter, more mobile tanks. Rather than serving as a fast-moving breakthrough vehicle, it was intended to dominate key areas of the battlefield through long-range engagement and defensive strength. Its heavy armor and powerful main gun made it well-suited to holding ground, countering enemy armor, and covering open terrain where visibility favored precision. In ideal conditions, the King Tiger could exert a strong presence. Its armor offered substantial protection, and its firepower allowed it to engage opponents at distances that reduced vulnerability. Crews operating under these circumstances could take advantage of the tank's design strengths, emphasizing deliberate movement and controlled engagement. However, ideal conditions were rare. By the time the King Tiger entered service in 1944, the broader strategic environment had changed dramatically. Resources were limited, fuel was scarce, and infrastructure was under constant strain. These factors shaped how, where, and how often the tank could be used. One of the most significant limitations was mobility. Although capable of movement, the King Tiger's immense weight restricted route options. Bridges often could not support its mass, forcing detours or limiting access altogether. Soft ground, mud, and damaged roads posed serious challenges, increasing the risk of immobilization. Logistics played a decisive role in operational effectiveness. The King Tiger required large quantities of fuel, spare parts, and maintenance support. Supplying these needs became increasingly difficult as supply lines were disrupted. Even a fully functional tank could become ineffective if fuel or parts were unavailable. Reliability issues further complicated operations. The complexity of the drivetrain, suspension, and engine systems meant that mechanical problems were not uncommon. Breakdowns could occur during movement, sometimes without warning. When a King Tiger became immobilized, recovery was difficult due to its size and weight. Maintenance demands were high. Regular inspection and repair were essential to keep the vehicle operational, but trained mechanics and tools were often in short supply. Field repairs were challenging, and major component failures could remove a tank from service for extended periods. The operational pace of the King Tiger was shaped by these constraints. Deployment required careful planning, route selection, and coordination with support units. Rapid redeployment or pursuit operations were rarely practical. Instead, the tank was most effective when positioned deliberately and used defensively or in controlled advances. Crew experience played a major role in operational outcomes. Well-trained crews could mitigate some limitations through careful operation and maintenance. Skilled drivers reduced mechanical strain, while experienced commanders made tactical choices that played to the tank's strengths. However, training standards varied. As the war progressed, shortages of experienced personnel affected crew proficiency. Operating a complex vehicle like the King Tiger required familiarity and discipline. Inexperienced crews faced a steep learning curve, increasing the likelihood of mechanical issues and operational inefficiencies. The psychological impact of operating such a heavy tank was also significant. Crews often had confidence in the vehicle's protection, which could influence decision-making. At the same time, awareness of mechanical fragility and fuel limitations introduced caution and stress. Environmental conditions further influenced operational use. Mud, snow, and extreme temperatures placed additional strain on mechanical systems. Cold weather affected lubrication and engine performance, while heat increased the risk of overheating. Each environment required adjustments in operation and maintenance. Operational strengths and weaknesses were closely intertwined. The very features that made the King Tiger formidable, heavy armor and powerful armament, also contributed to its limitations. Increased weight reduced mobility and increased fuel consumption. Complex systems improved capability but reduced reliability. From a strategic perspective, the King Tiger represented a concentrated investment of resources. Producing and maintaining such a vehicle required significant industrial and logistical support. In contrast, opposing forces often emphasized quantity, reliability, and ease of maintenance. This contrast influenced battlefield outcomes. While individual King Tigers could perform effectively in certain scenarios, their limited numbers and operational challenges reduced overall impact. The tank's presence was impressive, but sustaining that presence proved difficult. Coordination with other units was essential. The King Tiger rarely operated alone. Support from infantry, reconnaissance, and logistics units was necessary to protect flanks, provide information, and ensure supply. When this coordination broke down, vulnerabilities increased. Fuel shortages frequently constrained operations. Tanks could be forced to abandon movement or repositioning plans due to lack of fuel. In some cases, otherwise functional vehicles were left behind when supplies ran out, underscoring the importance of logistics. Repair and recovery limitations had long-term effects. A disabled King Tiger was not easily recovered under field conditions. Specialized recovery vehicles were required, and even then, success was not guaranteed. This reality increased the consequences of mechanical failure. Despite these challenges, the King Tiger did see operational use and demonstrated its design intent under certain conditions. Its armor could provide effective protection, and its firepower allowed for controlled engagement at range. These attributes made it a formidable opponent when circumstances aligned. However, its operational history also illustrates the limits of pushing engineering to extremes. Reliability issues and logistical demands offset potential advantages. The balance between innovation and practicality became a defining theme. From a historical perspective, the King Tiger's operational use provides valuable lessons. It highlights the importance of sustainability in military design. A vehicle's effectiveness depends not only on technical performance, but on the ability to deploy, maintain, and support it over time. Modern armored vehicle design reflects these lessons. Emphasis has shifted toward reliability, modularity, and ease of maintenance, alongside protection and firepower. The King Tiger represents a stage in this evolutionary process. It is important to approach this topic with a neutral, analytical perspective. Examining operational use does not require focusing on destruction or combat outcomes. Instead, it offers insight into how complex systems perform under real-world constraints. The King Tiger's story is not one of failure or success alone. It is a story of ambition, innovation, and the challenges of implementation. Its strengths were real, but so were its limitations. Understanding these factors helps explain why the King Tiger remains a subject of fascination. It embodies both the potential and the pitfalls of extreme engineering. Its legacy is defined by contrast, formidable capability paired with significant constraint. As we look back, the King Tiger serves as a reminder that engineering does not exist in isolation. Design choices interact with logistics, training, environment, and strategy. Ignoring any one of these factors can undermine even the most impressive machine. In the context of this series, examining operational use and limitations brings together many of the elements discussed so far. Armor, firepower, engine systems, drivetrain, and crew environment all converge in real-world operation. The experiences of crews operating the King Tiger reflect this convergence. Success depended on coordination, discipline, and adaptability. Limitations required constant adjustment and careful planning. By understanding how the King Tiger was actually used, we gain a more complete picture of the vehicle. It becomes more than a collection of specifications, it becomes a system shaped by context. As we move into the final chapter, we will step back and consider the King Tiger's overall legacy. By examining what it represents in the broader history of armored vehicle development, we can better understand why it continues to capture attention decades later. The King Tiger remains one of the most fascinating armored vehicles ever built. Not because it was flawless, and not because it changed the outcome of history on its own, but because it represents the outer limits of engineering ambition during a critical moment in time. Few machines better illustrate the tension between what was technically possible and what was practically sustainable. Throughout this exploration, we have stepped inside the King Tiger to understand more than just its appearance or reputation. We have examined its armor, its firepower, its mechanical systems, and the environment experienced by the crew. Together, these elements reveal a vehicle that was as complex as it was imposing. The King Tiger was designed at a moment when armored warfare had reached an intense stage of evolution. Firepower was increasing rapidly, and protection had to keep pace. Engineers responded by pushing armor thickness, gun capability, and mechanical complexity to unprecedented levels. In doing so, they created a vehicle that stood apart from anything else on the battlefield. However, this pursuit of maximum performance came with unavoidable trade-offs. Every increase in armor thickness added weight. Every enhancement in firepower demanded more space, stronger mounts, and additional support systems. The result was a tank that required extraordinary effort simply to operate and sustain. From the perspective of engineering history, the King Tiger serves as a case study in extremes. It demonstrates what happens when design priorities focus heavily on survivability and firepower, even when those priorities strain other aspects of performance. The vehicle was formidable in certain conditions, but demanding in nearly all of them. The interior of the King Tiger tells much of this story. Inside its armored shell, crew members worked in confined spaces, surrounded by machinery, ammunition, and structural components. Every role required discipline, coordination, and endurance. Comfort and convenience were secondary to functionality and protection. For the crew, operating the King Tiger was as much a physical challenge as a technical one. Steering heavy controls, managing heat and noise, handling large ammunition, and maintaining constant awareness of mechanical condition demanded focus and resilience. The tank rewarded careful operation, but punished mistakes. The mechanical systems we examined, from engine and cooling to drivetrain and suspension, highlight the complexity of sustaining such a vehicle. Each system relied on the others, forming an interconnected network where failure in one area could affect the whole. This interdependence increased the burden on crews and maintenance personnel alike. Logistical realities further shaped the King Tiger's legacy. Fuel consumption, maintenance demands, and recovery challenges limited how often and how effectively the tank could be deployed. In an environment where resources were increasingly constrained, sustaining such a complex machine became a significant challenge. Yet it would be a mistake to view the King Tiger solely through the lens of limitation. Its design reflected genuine innovation. Angled armor, advanced optics, and powerful armament represented important steps in armored vehicle development. Many of these ideas influenced later designs, even as engineers sought better balance. The King Tiger's impact can also be measured in how it shaped thinking about armored warfare. Its strengths demonstrated the value of protection and precision. Its weaknesses highlighted the importance of reliability, mobility, and logistical support. Together, these lessons informed future generations of vehicle design. Modern armored vehicles reflect a more balanced approach. Advances in materials, engines, electronics, and ergonomics have allowed designers to achieve protection and firepower without the same degree of compromise. Yet the fundamental challenges remain: balancing weight, mobility, survivability, and sustainability. In this sense, the King Tiger represents a transitional moment. It stands between earlier armored vehicles and the more refined designs that followed. Studying it helps us understand how engineering priorities evolve in response to experience and constraint. The fascination with the King Tiger also stems from its symbolic power. Its massive presence, distinctive shape, and reputation have made it an enduring subject of historical interest. Museums, restorations, and documentaries continue to draw attention, not because the tank was common, but because it was exceptional. Importantly, understanding the King Tiger does not require glorifying conflict. Instead, it invites us to examine how human ingenuity responds under pressure. Engineers, designers, and crews worked within the limits of their time, making choices that reflected both ambition and necessity. By examining what was inside the King Tiger, we move beyond myth and stereotype. The tank becomes a tangible example of how design decisions affect real people and real outcomes. It reminds us that machines are not just collections of parts, but systems shaped by context. The King Tiger's legacy also underscores the importance of adaptability. No design exists in a vacuum. A vehicle must operate within infrastructure, supply networks, and human capability. When any of these elements fall out of balance, even the most impressive machine can struggle. From a historical perspective, the King Tiger offers valuable insight into late war development pressures. It shows how urgency can drive innovation, but also how limited time and resources can constrain refinement and testing. The lessons drawn from the King Tiger extend beyond military history. They apply to engineering as a whole. Pushing boundaries can yield breakthroughs, but it also exposes weaknesses. Sustainable design requires balance, foresight, and an understanding of real-world conditions. As we conclude this series, the King Tiger stands as both an achievement and a cautionary example. Its armor, gun, and presence captured attention, but its complexity and demands shaped its fate. Neither aspect can be understood without the other. The tank's story is not about perfection. It is about ambition, constraint, and consequence. It reminds us that engineering decisions ripple outward, influencing not only performance, but usability, maintenance, and longevity. By stepping inside the King Tiger, examining its crew environment, mechanical systems, and operational reality, we gain a deeper appreciation for how machines reflect the priorities of their time. We see how design choices are shaped by pressure, resources, and expectations. In the end, the King Tiger remains memorable not because it solved every problem, but because it revealed so many. It showed what was possible, and what was difficult, when technology was pushed to its limits. Understanding the King Tiger helps us better understand history itself. It illustrates how innovation and limitation coexist, how ambition drives progress, and how balance ultimately determines success. This is the legacy of the King Tiger, a machine that invites study, reflection, and respect for the complexity of engineering under extreme conditions. Not a symbol of perfection, but a powerful reminder of how design choices shape both machines and the moments in which they exist.